What's up everyone? We're back here to continue learning about some basics of 3D, including rendering and the render pipeline. Let's jump right in with a recap of what I gave in an earlier presentation to get everyone caught up. Here we have a cube. The cube is what we call a 3D model. If you remember from the last presentation, this model is a cohesive object, but it's made up of vertices, which are points in space, edges, which connect the points in space, and faces, which are these byproduct shapes made up of the connections of vertices and edges. In this little animation, we can see the labeled vertices, edges, and faces of our model. Now these vertices, edges, and faces combine to make the model's mesh, which is how we texture the object. This cube, as you can see when the vertices, edges, and faces move away, is textured with a blue material. Looking at this simple scene, we have a model and a camera. We are viewing the model through the camera. What we are seeing on screen right now is from the camera's perspective. If we break the fourth wall, we are now looking at the scene we are just rendering from afar, and we can see the camera pointed at the cube to render the perspective that we are just seeing on the screen. But let's bring in a new scene. You may be wondering, how does the camera know what parts of the scene to render? This transparent cone is the field of view of the camera. Just like looking through a real camera, there are constraints to how much the camera can capture. For photographers and physical camera users, it's sort of like changing your field of view when you switch lenses or using your zooms. In 3D, we can change the field of view by simply scaling up the camera. In rendering terms, we call what the camera sees the view frustum. The view frustum is an area of space bounded by clip planes. These planes are not physical objects like I'm showing in my example with these green planes. They are more like mathematical constructs that determine what from your scene will get deleted. If you have models or parts of models in front of the near clip plane, they do not get rendered because they're too close to the camera. If you have models or parts of models behind the far clip plane, they also do not get rendered because they're too far away for the camera to see. The other boundary of the view frustum is just the field of view of the camera, which is what the cone is representing in my demo. Anything outside of this cone or not between the two clip planes does not get rendered. So if I add these two cubes to the scene, neither of them would get rendered since they're both outside of the view frustum, one being in front of the near clip plane, one being outside of the field of view. Even though there are 3 objects in my scene, only one gets rendered, which is that pink sphere. This decision, as well as many others, are just calculations made within the render pipeline. We know from the last presentation that rendering is the process of taking these 3D models and converting them to 2D pixel images. Similar to what my animation is doing, taking that 3D model in space and flattening it to a 2D pixeled circle. But how is that done? Through the render pipeline. The render pipeline is just the formal reference to the series of steps the computer takes to make that conversion. These steps are called on every model, every frame, so this pipeline is called a lot. There are 5 basic steps that take a model from 3D points in space to 2D pixels on screen. Let's take a quick look at those steps. The first stage of the render pipeline is the input assembler stage. The input assembler stage does just that. It assembles all the necessary inputs to start up the render pipeline. These inputs are things like the model's vertices, which we represented with these red points in space, and the layout of what information is stored in each vertex. The second stage is the vertex shader stage. Here, operations are performed on every single one of the model's vertices. First, the vertex coordinates are converted from local space to camera space, which is a process that doesn't physically move the model's vertices in space, it just places the vertices in the same coordinate system of the camera so we can later move the vertices with respect to the camera. Now that process may sound complicated, but let's visualize it. Let's take the top point of the pyramid. In local coordinate space, that point is at 0, 1, 0. 0 in the x direction, 1 in the y direction, and 0 in the z direction. Let's view that. 0 in the x, 1 in the y, 0 in the z. However, in the camera's coordinate system, that same point at the top of the pyramid may be at 2 units in the x direction, 6 units in the y direction, and 25 units in the z direction. This point did not move in physical space, it just got relabeled in a different coordinate system, which is the camera coordinate system. This stage also applies things like color and texture to the vertices. So in this instance, we've applied the color blue. At the end of this stage, we have a model in the same coordinate system as the camera and with the correct color and texture mapped to it. The third stage is the Rasterizer Stage. To rasterize is to pixelate, but there's a few things that can happen before we can turn this 3D model into 2D pixels. To get to the Rasterizer Stage, we will have gone through a clipping stage. So what happens there is that any parts of the model outside the camera's view, or outside of that view frustum that we learned about earlier, they get deleted. In our example, our pyramid is fully within the view frustum, or what I colored in this cone. But let's say the top of our pyramid was outside of the view frustum. Then the top of that pyramid would just be deleted. It's outside the camera's view, so it wouldn't be rendered anyway, so we can safely delete it. So our pyramid would then look like this. Within the rasterizer stage, though, we perform something called backface culling. This is the process where all of the faces on the back side of the model that are not seen because of the camera's perspective get deleted. So for our pyramid, that would mean deleting those 2 back faces that the camera does not see and would not get rendered out to the final image. The next thing to happen is that all of the vertices are moved to a space which is the same dimensions of the viewport we are rendering to, which we can do thanks to those camera coordinates we figured out in the second render pipeline stage. This is done through the use of an NDC and homogeneous coordinate division, but we won't get into the details of that. All we really need to know is that the vertices are moved to this space which is the same dimensions of the viewport we're rendering to. The final job of this stage is to transform all the faces that are left, which are now only the faces that the camera can see and will be rendered, transforming those faces into pixels, and then adding all effects like color and texture to those pixels. So in this animation, we're flattening our 3D model, all of those faces that are left, into 2D pixels. For the sake of the demo, our faces aren't exactly flattened into the 2D pixels, but just for sake of visualization, just imagine that these faces that are left are now flat 2D pixels. So at the end of this third stage, our model has been transformed into 2D pixels, which these are only the pixels that we can see from the camera view. They are resized to the shape of the viewport and they are colored and textured the same way the original 3D model was. Moving on to the fourth stage, which is the pixel shader stage. The pixel shader stage is mathematically intense, but it can be explained very simply. This stage takes all the pixels and applies lighting effects to them, so now the pixels are colored and textured, but also shaded and lit. So say there was this red spotlight in our scene. The pixel shader stage is where that red lighting effect would be added to the blue pixels, creating that pink shading. The fifth and final stage is the output merger stage. This stage applies any last blending or transparency effects to the pixels and also determines the depth of the pixels. This, what they call depth buffering, is really important since each model goes through the rendering pipeline alone. Up until this point, we have no way of determining if the object we are rendering is fully visible or if it's obscured by an object closer to the camera. Say, for instance, this sphere is also in my scene. Well, what does the camera see now? The sphere is fully blocking the pyramid from the camera's perspective. So all the camera sees now is the sphere pixels and no longer sees the pyramid pixels. So it would get rendered out as just the sphere pixel, not the pyramid pixels. But let's take out the sphere because we've come so far with our pyramid. Once this depth is computed, all our final pixels then get drawn onto our render target, which is presented in the viewport, and voila! We have a rendered image of a 3D scene into a 2D image. Just to render out the single pyramid, we see how much behind-the-scenes math and computation goes into rendering, which I find fascinating and I hope you do too. Thank you.